If you've taken a course in calculus or analysis, then you'll know what the derivative of a function is, and you'll have come across a differential equation. And if you know what both of those are, then you'll also know that the function mod x, or the absolute value of x, definitely isn't differentiable. Or is it? I mean, look at the point at x equals 0. It's a sharp corner, certainly too sharp to be differentiable. And if you're still not convinced, then we can even check using the limit definition of the derivative at the point x equals 0. Taking the limit from the negative side, we get that it's equal to -1. And if we do the same thing from the positive side, then we get that it's equal to +1. See? The left and right hand limits don't agree, so we can be absolutely certain that it isn't differentiable. Since we agree that mod x is certainly not differentiable, then this differential equation here certainly doesn't have a solution g. This means it still won't have a solution even if I multiply both sides by a not suspicious at all function that has the properties that it's a, differentiable infinitely many times, and b, equal to 0 at the points -1 and 1, as well as equal to 0 anywhere outside the interval -1 to 1. Multiplying both sides of the differential equation by the same thing certainly won't just magic a new solution out of thin air. Neither will integrating both sides over the interval -1 to 1, because that would just be silly. Even if I use my favourite integration by parts formula over here on the left-hand side, it's not going to change anything. I mean, sure, this little term over here disappears because 5 minus 1 and 5, 1 were equal to 0, but this integral equation I have now must be impossible to solve. Let's not forget, f here is mod x, so this can't have any solution, because it's just the same as this differential equation. And we know that mod x doesn't have a derivative, right? Well, if you've watched this far, I'm sure you realise that there's something dubious going on here. It turns out that we can in fact find a solution to this integral equation. If I take the following function for g, which happens to be more commonly known as the sine function, and we plug this into our equation, watch what happens. We'll deal with the right-hand side first, as it works out being a bit simpler. We split the integral into two parts, the integral from -1 to 0, plus the integral from 0 to 1. Now, if we substitute in our sine function for g, we get the integral from -1 to 0 of -phi, plus the integral from 0 to 1 of +phi. You might worry about what happens at the point 0. We know that changing the value of a function at one point doesn't change the value of the integral, so we can just leave it like this. So, with g as the sine function, the right-hand side becomes the sum of these two integrals. Next, we'll take a look at the left-hand side, and this one takes a bit more work. Again, we're going to split this up into the sum of two integrals, one from -1 to 0, and the other from 0 to 1. And here we've replaced mod x with -x for the integral over the negative values, and plus x over the positive values, so all is still good. Let's consider this first term here. If we perform an integration by parts, it leads to this. Notice, however, that this term is just going to be equal to 0, because at x equals 0, we'll have 0 times 5, 0, and that's always going to come out as 0. And at x equals -1, well, we made sure that phi had the property that 5 minus 1 was equal to 0. So that means that both of these cases are equal to 0, so the whole term is going to vanish, leaving us with just the integral term. Now we can deal with the second integral in the line above. Once again, we'll integrate by parts, and a similar thing happens. Again, this term here is going to become 0, for the same reason as before, because we also made sure that 5, 1 was equal to 0. So we're just left with this integral term. Now, things are starting to look a bit familiar, but let's not forget that we had a minus in front of all of this, so let's bring that over too. Now that we've accounted for this minus sign, look what we end up with. This is the same thing that came out when we substituted in the sine function for g on the other side. So what this shows is that actually the sine function solves our integral equation. But the question is, does this mean that it solves the differential equation that we started with? The answer, as with many things in mathematics, is it depends. Using what we said at the beginning of the video with the definition of the derivative, the answer is still unfortunately no. But what mathematicians do sometimes to try and solve seemingly impossible or nonsensical problems is to kind of tinker with the rules a little bit. What I did with the original differential equation, multiplying it by phi and integrating and so on and so forth, that's called a reformulation of the original problem. And it comes with extra solutions. If we took a function that actually had a derivative, and I plugged that function and its derivative into the integral equation we had, then everything would still work out. If you don't believe me, then let's look at a super easy example. We know that the derivative of x squared is 2x, so let's put these two into our equation and check that both sides agree. So now you can hopefully believe me that if we can solve the differential equation, we can definitely solve the integral equation. However, the converse isn't true. Just because I have two functions that solve this integral equation doesn't mean that one of them is the derivative of the other. And we actually showed this at the start with our absolute value of x function. This is what is known as a weak derivative. Let's take a look at the precise definition that mathematicians use. It reads as follows. Let f be an integrable function. Then an integrable function g is called a weak derivative of f over the integral ab if the integral over ab of f times the derivative of phi is equal to minus the integral over ab of g times phi. For every function phi which is infinitely differentiable and equal to 0 outside of ab. This definition is kind of technical, but we can break it down. A key point is that we say f and g should be integrable functions. This lines up with our idea of what we did earlier, because we integrated mod x and we integrated the sine function. We didn't differentiate them. It's worth highlighting here that there are a lot more functions which are integrable than there are functions which are differentiable. We won't go into too much detail on this now, but to give you a quick idea as to why this is true, you should know that any differentiable function is always continuous, and therefore it's integrable. On the other hand, we can also integrate functions which aren't continuous, but we can't differentiate those functions. Going back to our definition, there's a couple of slight differences between the integral equation we have here and the integral equation that we were solving earlier. First, we've written phi prime here to denote its derivative with respect to x, and secondly, we shift the minus sign over to the integral on the right hand side. Now, these differences are more conventional rather than anything significant to the maths. Finally, and most importantly, we have this statement at the bottom, which says that this integral equation must hold for every phi that has these conditions. These conditions are the same as what I gave my phi from earlier, except that here we took any interval ab instead of minus 1 to 1 that I used before. We call these phi test functions. This is important because it keeps the formulation general enough to actually give the solutions we find some meaning. Alternatively, we sometimes take a function g and form the differential equation, and then try to solve for a solution f of the integral equation. If a function f solves the integral equation for a given g, we say that f is a weak solution of that differential equation. And again, this must also hold for any phi with the properties that we had before. Why would we want to do this though? Well, in a general sense, this is an example of a mathematical abstraction or a generalization, which is where mathematicians loosen the rules a bit to try and be able to talk about a broader collection of things. In our case, we were able to look for a solution in the set of all integrable functions, which is much bigger than the set of differentiable functions that we were previously looking in. Weak solutions and weak derivatives are a helpful alternative to consider in the event that we can't find any normal derivatives or solutions. One of the biggest areas that mathematicians have historically dealt with is differential equations. A lot of times differential equations can be difficult or even impossible to solve, especially partial differential equations. But a lot of them arise from natural things that we observe in the real world, and even if we can't find a nice normal solution to them, finding a weak solution can still give us some insight into whatever system or process is being modelled. The study of partial differential equations through means of weak derivatives and weak solutions came into practice during the 20th century, and what we've looked at here isn't actually the only type of weak solution. The term weak solution is often used to describe a variety of different reformulations of the problem that we studied earlier. And the different kinds of weak solutions you find tell you different information about the differential equation that you're working with. Hopefully, now you've seen a little bit beyond the horizons of what you'll have covered in your Intro to Analysis or Calculus class, and hopefully you also gained some insight into the way a more advanced mathematician might think about their problems. I'd really encourage you to look into the stuff I've talked about online if you're up for a challenge, because it is quite tough. The study of partial differential equations is a vast area, and there's so much more to be discovered than what I can squeeze into a short video like this one. But that's all I have for now, so until next time, thanks for watching.